1 amp for my current, 1 for my length, and B is 1, so it's 1 times 1 times 0.1 is 0.1 newtons on those trading things right there. Actually, no, it's very much makes sense if you don't skip any graphs. The recap on this. First, you draw the picture of whatever your shape is. You look at it going in. You look how the current goes based on Lenz's law. What is Lenz's law? An induced current always flows in such a sense as to oppose the change that creates it. So if there's an increasing flux, it tries to make it not increase, so it flows opposite. If there's a decreasing flux, it tries to keep it the same, so it goes in the same sense. So it'll try to oppose the change. It doesn't try to oppose the field, it doesn't try to oppose the current, it tries to oppose the change. If flux is increasing, it tries to prevent it from increasing. If flux is decreasing, it tries to prevent it from decreasing. Okay? So with that all put together, it's really quite simple. The easiest one in the world to draw is the flux. You just look at it and you say, what's the areas involved? And the shapes that you'll be given will be very straightforward geometrical shapes. So you can say on this one, 0 till it gets in, then I get the full 3 once that part's in, draw a dot, then I get the full 4 once the next one's in. So I made a dot at the 3, I made a dot at the 4, and then I just connect straight lines. Once it's in, the total flux never changes. On the way out, the big one comes out first, dropping it by 3, then the small one comes out, dropping it by the last one. Now that you've got this, how do I get this? You just find the slopes. What's the slope going from 1 to 3 along 1 second? 3. So minus 3 is my EMF because it's that minus sign in the equation. And what's the slope going from 3 to 4 in 1 second? 1. Because it changes by 1 in each direction. So I get minus 1 is my EMF. Then nothing when the slope isn't changing. And then I change from 4 to 3, which means I have a negative 3, but the negative sign forces to a positive 3. And the same way I have a negative 1, positive 1. Now I have my EMF. You all see how I get that. Now that I have my EMF, it's really easy to find my current. I just find out what's the total resistance of my loop. If it were 27, fine. You just divide everything here by 27. Whatever the total resistance of your loop is, you take your EMF and divide by the resistance to get the current. Whose law is that?
Ohm's law. Just
Ohm's law, right? It's just Ohm's law. That's all this is if I know the EMF and I know the resistance, I can find the current. All right? So I get the current. Now that I have the current, to find the force, I just come here. I know the current for the first 3 seconds. I know the length of wire that's being acted on, and I know the B field. So I can find the force that I need to have that happen there. All right? And then for the next second, I have a new current, I have a new length, and I recalculate.
For our loop on the test, you're not going to give us like a triangle, right?
I would shoot myself rather than try to grade that because you'd have to use some calculus. And I know some people have had calculus, but no, that's not going to happen. There'll be nothing but vertical and horizontal wires. No angles.
Okay.
I can see it now. I'm going to do a isosceles triangle rotated 37 degrees from right.
I'll take the W.
Yeah. My intent is to make this easy enough that I can grade it, but hard enough so that it's worth studying. Okay? So, now, having done all that, there's a couple other things I want to talk to you about. So, we have done several problems now in terms of Faraday's law, Lenz's law, and all that good stuff. You probably want to know these a little bit by name. So remind me, what is Lenz's law? We just said it, but let's rewind. All right, no. So, no, actually, that is cool. All right, so go ahead and say it so we can all listen. Yeah, I scared the reading right out of you. Go ahead.
So when there's a change in magnetic flux, the induced current will flow to its 100%.
Exactly. When there's a change in the magnetic flux, the induced current will flow in such a way as to try to prevent the change. If the flux is decreasing, the current flows to try to keep it higher. If it's increasing, we try to prevent it from increasing. All right, so we'll try to prevent the change. Faraday's law. Oh, that's this one. a change in flux results in an EMF. All right, you're not going to do very much with this, but because I preached so much about it last semester and this semester, remember I told you that this semester electric fields are conservative so that we could use all the rules we had about conservative forces and fields and stuff from last semester? This ain't conservative. So this EMF that comes from a change in magnetic flux is not conservative. And if that doesn't break your brain, you're not thinking very hard. Because how can nature say there's two kinds of electric field, one that's conservative and one that isn't? Because it's electric field. Electrons behave the same in it no matter what. But it isn't. It's not conservative. All right? And one of the ways that you can see this is if I had a wire in a magnetic field that's decreasing, and there would be a current flowing in this wire, right? But there's no battery. So if I do Kirchhoff's rule and I go all the way around and say the sum of voltage ought to be 0, is it? No, because there's no battery. All I do is either go completely up the whole way around or completely down all the way around, but there's no battery to boost me back to 0. So a closed loop is not going to give me 0 anymore. Yeah. And when you sort that out and have an answer for it, please whisper it to me and I'll pretend like I said it first. All right, so we just have non-conservative forces when we're dealing with Faraday's law. All right, and so when I say there's no such thing as a magnetic monopole, what does that mean? You can never just have one. You can't just have a north pole. You can't just have a south pole. They always come north and south together. How is that different from electrostatics at the beginning? Could you have a monocharge?
Yes.
Yes, you can have just a positive or just a negative. So I can have, I don't always have to be balanced. All right, so I can have something that has a net positive charge or has a net negative charge, but I can never have anything that's just a net north. Although Stanford has twice claimed to have discovered a magnetic monopole, it never lasts long enough to become text. So people keep looking because they think it'd be cool if they could figure it out, but so far nobody's been able to. All right, so any questions you have about either chapter 17 or 18 so far?
What was the original question? The last part you just finished?
The original question on?
What you just went over, magnetic pole.
I said, can we ever have a magnetic monopole? Can you ever just have a north or just a south? And the answer is no. All right, so we're kind of late for our lab, I know, but the lab's going to go very fast. So let's go do it. All four of us. Let it shoot.